Darcy's law can be written as V equals K times I, where V is the rate of the groundwater flow, K is the hydraulic conductivity, and I is the hydraulic gradient. Because of the way this equation is written, if you know at least two of the variables, you can figure out the other one. In our practice example, we are going to take the scenario of a hillside, and we're going to determine the groundwater rate between the first drill hole and the second drill hole. One is at the top of the hill, one is at the bottom of the hill. Now the materials that are comprising the hill have a hydraulic conductivity of 0.00002 meters per second. The elevation at the top of the hill is 128 meters above sea level. The elevation at the bottom of the hill is 113 meters above sea level. And the distance between the 2 points is 804 meters. With this information, everything is in the same units, meaning everything is in meters. We don't have to convert anything to get everything into the same unit. So basically, we can just plug and chug this information into Darcy's law to get our groundwater rate. So on the left, we have all of our information that we've been given to complete this problem, and one thing that's missing is I, or the hydraulic gradient. So that's the first thing we need to do, is calculate the hydraulic gradient. We have everything we need to do this. So we take the elevation differences between drill hole 1 and drill hole 2 and divide it by the distance that separates them. So 15 meters elevation difference divided by 804 meters, which is the distance between them, gives us a hydraulic gradient of 0.01865. So this is our I value. So we can replace the information that we were given with the I that we have calculated. Now the second thing we need to do is plug and chug. So we will plug in our values for K and I to calculate our flow rate. This gives us an answer of 0.000000373 meters per second. That is how fast drops of groundwater are moving from the top of the hill to the bottom of the hill every second. Now, at step 2, you have calculated Darcy's law, but we can take this a step further. Once you have calculated the flow rate, we can actually begin to step by step convert this answer into something that is more manageable or comprehensible. So our first step, since our answer is in meters per second, will be to convert it into meters per minute. This will let us know how fast the groundwater is moving in terms of meters per minute. So in order to do this, we need to work with the conversion factor, and our conversion factor is that 1 minute equals 60 seconds. So all we have to do to convert our answer from seconds to minutes is to multiply by 60. In the next step, we can convert from minutes to hours, and our conversion factor is that 1 hour equals 60 minutes. So we take our answer in meters per minute and multiply it by 60 minutes. This will give us our answer in meters per hour. The next step is to convert from hours to days. And so there are 24 hours in one day, so we simply multiply our answer that is in meters per hour by 24 hours. This will tell us how fast the groundwater is moving in meters every day. Finally, we want to convert our answer into years. So how fast is that groundwater moving every year? So let's take our answer in meters per day and multiply it by 365, because that's how many days there are in a year. This conversion will tell us how far the groundwater has moved in a year. So why did we go through all of that trouble? What does this really tell us? So it tells us that a groundwater flow rate of 11.76 meters per year and a distance between 2 points, those 2 drill holes, of 804 meters. If we take these numbers and divide them, it will tell us that it takes a drop of groundwater almost 70 years to move from point A to point B. This is the main point of Darcy's law. This is how hydrogeologists and petroleum geologists use this equation. They need to know how long it's going to take for the groundwater or the petroleum deposit to make it from point A to point B. This equation alone is responsible for delivering you groundwater to your home and extracting petroleum deposits that go into making your gasoline and your diesel and your natural gas that you use for fuel. Without this equation, there would be a lot fewer resources for groundwater and petroleum deposits simply because we wouldn't know how to get them out of the ground. If you have any questions about this equation, don't hesitate to let me know. As you all know, I'm here to help you, especially here in the last lab module of the semester.